So now we're going to dive more specifically into zeros and find zeros of polynomials and then talk about one characteristic of zeros, which is called their multiplicity. Okay? So now more than just like saying the possible number of real zeros and things that a polynomial function can have, you can see that here we're going to try to actually find all the zeros of the function. So since a zero is going to be an x value that makes the y value 0, then to find a 0, you'd want to plug in 0 for y, right? So then you can find the x or x's that can make y equal 0. So we'll want to plug in 0 for f of x then, for y. And then this equation right here is an equation that we'll want to solve for x, okay? So you'll notice that we do have 4 separate terms that are set equal to 0 right here. So we might be able to factor this by grouping. So if we group these first couple of terms together, we'd want to factor out the GCF of just those 2 terms. The most that you could factor out of x to the third and x squared would be x squared. So by taking out x squared, then you'd be left with x plus 1 inside of the parentheses there. Okay. And then if I were to group the other 2 terms together, I'd be able to take out a negative 4 from both negative 4x and negative 4. That's the greatest. So then I can put plus negative 4 times x plus 1. And then that blue term and that red term both have the common factor of x plus 1 that I can factor out from both of them. And so then we get the right-hand side of the equal sign here to now be completely factored as the product of this binomial x plus 1 with the binomial x squared minus 4. Okay? And that's really helpful because then we can use the zero product property to solve. You'll notice that actually, like then this one right here though, is x squared minus 4, which is a difference of squares. It's x squared minus 2 squared. So you could break that down further into x plus 2 times x minus 2. So then correspondingly, negative 1 and negative 2 and positive 2 are going to be the solutions to the equation, and therefore will be the zeros of the function. And this is actually the graph of f, and you'll see that at negative 2 and negative 1 and 2 are actually where the x-intercepts are, and whenever there's an x-intercept, those are going to correspond to the zeros that are the real ones, and that's exactly what we came up with. Okay. Another nice little example right here where we want to try to find zeros is this guy right here. So we'll see, the answers show up on the graph a little bit, but you need to be able to do this without a graph because with the problems, you're not going to have a graph to look at, right? So we want to find the zeros. So that just means that you want to plug in 0 for y, right? And then solve for the x's that can make y equal 0. Okay, so then we need to solve this equation right here. Cool. So I think with this example, there's actually supposed to be an x right there. So yeah, make there be an x right there. That's just a typo on my part. Okay, so of all of the terms in this polynomial, all 3 terms in this trinomial, there is a GCF we can take out of all the terms. So whenever we're factoring, we want to do so. So 4, 48, and 144 are probably all divisible by 4. Yeah, they all are. So we can take out a 4. Now, I would also recommend that because the highest degree term, was the 3 right there, has a negative leading coefficient, that you should actually factor out a negative. It's typically what we'll do. So I would factor out a negative 4 from everything. But also, each term does have at least a variable. There's x to the third, x squared, and x. So then I'd also factor out an x. So if you take out negative 4x from all the terms, then you'd be left with x squared minus 48 divided by 4 is 12x, and 144 divided by 4 is 36, so that'd be plus 36. Okay, so that's what we get when we take out negative 4x. Then you'll notice this one right here. You'll see that the last term is 6 times 6, and then this one right here is negative 6 plus negative 6. So then that's pretty special, right? That's actually a perfect square trinomial. So that's going to factor as x minus 6 times x minus 6. So further factoring that right-hand side gets us to there. Now you could write it as x minus 6 squared, right? But then at this point, now that that right-hand side is completely factored and the product equals 0, then you can use the zero product property. So from this right here, we're going to get x equals 6 as an answer, but technically you get that like twice, right? And then right here, because negative 4 times x is equal to 0, then x equals 0 would be another real 0. So it turns out that only those numbers of 0 and 6 will be the only x-intercepts, or the only real zeros of the graph, okay? But this one was a little bit different in the fact that you did get x equals 6 as an answer twice. And so what we would say there is if you do get an answer twice or 3 times or more, is then it has multiplicity of that. So in this case it would have multiplicity 2 because it showed up as an answer twice, okay? And an interesting thing that then happens in the graph is that then it actually like touches or it bounces on the x-axis when it has an even multiplicity like that. Versus like right here, it actually crosses through the x-axis because there it had multiplicity 1. We do say it has multiplicity 1 when it only shows up as a 0 once. Yeah, that whenever it has an odd multiplicity, it can actually just cross through the graph, okay? So it's this idea of multiplicity of zeros. Multiplicity just tells you like the number of times the 0 like is a 0 in the graph, right? So it'll be multiplicity 4 if it's a 0 4 times, right? And just know that if it is a 0 of even multiplicity, that it's going to like just touch or bounce, in other words, on the x-axis at that particular 0 number. And then if it is of odd multiplicity, it's going to cross through the x-axis. So it's going to like come from above and then go into the negative part, or it's going to come from the negative part and then go into the positive part above the x-axis. Yeah, so that's what happens with like that. All right, so here we want to find the zeros and their multiplicities for each of the given functions. So you can see this is already factored, right? So when you plug in a 0 right there for y, it's pretty easy to find the zeros. So you're going to get x equals 0 is going to be a 0. And then also x equals negative 6 is going to be a 0. And then right there you got 3x plus 7. So if you set 3x plus 7 equals 0, you would subtract 7 and divide by 3. So negative 7/3 would be another 0 of the function, something you could plug in that would make the y value equal to 0, right? Okay, so that's going to be a 0, that's going to be a 0, that's going to be a 0. But we're asked to also find the multiplicities of each of these zeros. So because there's really just an exponent of 1 on the x, then x equals 0 is going to be a 0 of multiplicity 1. Because x plus 6 showed up as a factor twice, then negative 6 is going to be a 0 of multiplicity 2. And then this right here had an exponent of 3, that factor. So negative 7/3 is actually a 0 3 times, so it's of multiplicity 3. Okay? All right, so for this one, find the zeros. It's not factored, so we will maybe try to factor it to help us solve for the zeros. So if we plug in 0 for y, then we have this equation. And then there is a GCF of these two terms, x to the 5th and 8x squared, because you can factor out just variable, not numbers. You can factor out x squared from both, and then you're left with x to the 3rd plus 8. So already right now you can tell that because now it's in a factored form, you've got x squared as one of the factors, that x equals 0 is going to be a 0 of the polynomial, and that's going to be specifically of multiplicity 2, because you got the exponent of 2 on the x. And then from here, we're going to be able to identify 3 more zeros, because the highest exponent there on x to the 3rd plus 8 is 3. So we need to get zeros, 3 more answers, I guess, right? So because it's x to the 3rd plus 8, you can think about that as being x to the 3rd plus 2 to the 3rd, which is a sum of cubes, right? So remember, factoring a sum of cubes, that then we could keep factoring this further then, where we will have the x and the 2 get added there. And then the second factor is going to be the square of x added with 2 times x. Or sorry, that's going to be opposite sign. Subtracted with 2 times x, and then 2 times 2 at the end will get added. So what should have happened there, right, is that SOAP idea that we should have had the same sign, the opposite sign, and then always plus, corresponding to the fact that it started out as plus, right? So same sign would be plus, opposite sign would be minus, and then always plus. Okay, so we already dealt with this right here, because we already indicated that it's going to have a 0 of 0 with multiplicity 2. So then we just need to worry about then this right here. So because you have x plus 2 as a factor, then x equals negative 2 is going to be a 0, and that's going to be a multiplicity just 1, because you only have x plus 2 show up once. And then the last factor that you have right there is x squared minus 2x plus 4. So remember that when you're doing factoring of a sum or difference of cubes, that factor is always prime. So then you're going to have to use quadratic formula on this, because x squared minus 2x plus 4 is quadratic to solve, and you're going to get some like funkier numbers for the zeros. So since your a is going to be 1, and b is negative 2, and c is equal to 4, then x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So then you get, that's going to be a positive 2 over 2 times 1 at the bottom is 2, plus or minus square root of something over 2. So inside that square root, you're going to have negative 2 squared is 4, and then 4 times 1 times 4 is 16. It's going to be subtracted. So then you get a negative 12 underneath that square root there. So that means you're going to get some imaginary zeros, right? Because you got that negative underneath the square root. So further simplifying a little bit right here, 2 over 2 is equal to 1. And then square root of negative 12 is the same thing as I squared of 12. But because 12 has a perfect square factor of 4, then you could simplify that by writing that as square root of 4 times square root of 3, because 4 times 3 is 12. But we know the square root of 4 is 2. So it becomes 2I squared root of 3 on top, over 2. But then 2 divided by 2 is 1, so then it becomes then just I squared 3 that gets added or subtracted from 1. So therefore then, we can say that we also have x equals 1 plus I squared 3. And then we can also say that we have x equals 1 minus I squared 3. So that's going to be multiplicity 1, and that's going to be multiplicity 1, because those zeros only show up once a piece as well. All right, so in total, we got 5 different answers, right? We got this number, we got this number, we got this number, and then we got that number twice, right? So 5 total answers, and that makes sense, because the highest exponent there was 5, of course, okay? So to help that all kind of make sense, you can see in the graphs for these 2 examples that we just did right here, that for this graph, we had at negative 6 and negative 7/3, and then at 0, the zeros, which is exactly what we got, 0, negative 6, and negative 7/3, okay? Now also keep in mind that right here, this happened with multiplicity 2, which means this was even multiplicity, and that's when at the 0 on the graph, it should bounce. So you'll see that right here at negative 6, it did bounce, right? So it's just stayed below the negative axis, x-axis there, but here it crossed, and then there it also crossed, because you had odd multiplicity of 1 or odd multiplicity of 3 for those ones, okay? So the same thing would have happened here, but actually since like these couple of zeros were imaginary, you're not going to see those on the graph, right? So the only actual x-intercepts you're going to see are going to be at 0 as well as negative 2. This was even multiplicity and this was odd multiplicity, so you should expect it to bounce at 0 but then cross at negative 2, which is exactly what's happening. At 0 it's bouncing, and then at negative 2 it's crossing. Okay. And there's just a couple more examples of being able to find zeros from the equation right here. So if you set 0 equal to x to the 4th minus 16, that's basically like a difference of squares, because this right here would be x squared squared, and this right here is the square of 4. So you could write this then as x squared minus 4 times x squared plus 4. And then, clearly, that right there is another difference, and it's x squared minus 2 squared. So that right there could be broken down to be x plus 2 times x minus 2. Okay? And then, because that's plus, you could kind of think about that as being x squared minus so then it's kind of like a difference of squares, but then since the square root of negative would be 2i, then you can actually factor that down as x plus 2i times x minus 2i when it's a sum of squares. So it's 100% true that that right there will multiply FOIL to be the same thing as x squared plus 4. You could totally check that out, like x times x is x squared. X times negative 2i is minus 2ix. X times 2i is plus 2ix. And 2i times negative 2i is negative 4i squared. But then because I squared is negative 1 times negative 4 is going to be plus 4. Those cancel because they just are opposites, so that's why it's x squared plus 4, right? So, because of all that then it's pretty easy to find all the zeros here, because you're going to have negative 2, you're going to have 2, and then you're going to have negative 2i, and then you're going to have 2i, all be the zeros. So all of those zeros all are just of multiplicity 1, because they are only zeros one time. So yeah, that's your zeros for that. And then the last one here. 2, 18, and 72 are all divisible by 2, so you could take out a 2, but I would also take out a negative, because the leading coefficient is negative. And then you also have x to the 6th and x to the 4th and x squared, so I would also factor out x squared from all the terms. It leaves you with x to the 4th plus 9x squared minus, because you took out a negative, and then 36 is half of 72. Cool. Alright, so then we have negative 2x squared. And then this right here, you could maybe try to factor it further. So you'd have to figure out what's going to multiply to equal 36, but add to 9. And I think if you did 12 times 3, that equals 36. But then if you wanted to add to 9, you could make the 3 be negative. And that would work, right? Because 12 plus negative 3 is positive 9, and 12 times negative 3 is negative 36. So you could do positive 12 and negative 3, and then x squared plus 12, x squared minus 3, right? Because there's x to the 4th plus x squared term plus constant term, right? Yeah, so from there, can kind of figure it out pretty easily from there. So this right here is x squared minus 3, so you could actually factor that as x plus the square root of 3 times x minus the square root of 3, if you kind of force 3 to be square rooted like that, so that totally works. And then similarly, this is plus, so you would want to like think about that as being like x plus I squared of 12, and then x minus I squared of 12. So you'll have the I there because it was plus originally with the x squared plus 12. But you can simplify the square root of 12 because that's actually going to be 2 square root of 3. So think about this as being x plus 2i square root of 3 and x minus 2i square root of 3. And so then, yeah, you can get all the zeros pretty okay. So right there, you're going to have x equals 0 of multiplicity 2. And then the rest of these are all going to be of multiplicity 1. You're going to get negative 2i square root of 3, and you're going to get positive 2i square root of 3, and negative square root of 3, and then square root of 3. So 4 zeros there, and then a 0 of 0 happens twice. Yeah, those are going to be all the zeros. Okay. And then also, analogously, I have the graphs of these two functions. You're only going to see the real ones show up. The imaginary ones you won't be able to see. So here you only see negative 2 and 2, because in that one, we only got negative 2 and 2 to be the real ones. The other ones were imaginary, right? And then here, you'll see that this is actually where negative square root 3 is, and this is where square root 3 is, because remember that square root 3 is about 1.73. So that's at negative 1.73 and 1.73, right? And then also at 0. And those were the only real ones we got for that one. 0 and negative square root 3 and square root 3, because the other two were imaginary, okay? And then the whole bouncing and crossing stuff matches up nicely too with the idea of being of odd multiplicity or even multiplicity as well. So just take note of that as well.